Sorry, let me just get my notes here. So this is our fourth of 5 seminars today. And as always, we'll be doing a live Q&A at the end of the session. So please feel free to submit your questions here in the GoToWebinar console, and we'll make sure to get answers to your questions time permitting. We're going to be sending completion certificates in a follow-up email next week. And if you have any technical issues, please feel free to email us at webinar@origin-and-cause.com. So I'd like to introduce our speakers. Our first speaker is Eduardo Mari. He has a degree in materials science and engineering, as well as 20 years of experience in engineering failure investigations and industrial field experience. He's led over 1,000 forensic engineering investigations and has been an expert witness, has provided expert witness testimony in several judicial proceedings and pre-hearings. And he specializes in plumbing and mechanical systems, fire sprinkler systems, product liability, fuel oil installations, personal injury from failure of mechanical components, and static equipment in O&G. We also have Dinu Matei joining us today with over 30 years of industry and academic experience, with over 200 forensic investigations having been conducted in his career. His mechanical and materials engineering specialties include failure analysis, product liability, commercial and residential plumbing systems and component failures, oil spills, corrosion, metallurgical and fractography investigations. So I'll pass off the mic to Eduardo to start us off.
Thank you, George. You can send over the control to me.
Yes, sir.
Okay, thanks everyone for attending the presentation today. Hopefully you're seeing my presentation and not my notes.
Yep, you're good.
Yeah, I will start by saying that materials and mechanical engineering are well known for investigations involving metals. However, more and more components are made out of plastics or different types of polymer today. Many cases of plastic failures require a much different understanding of failure mechanisms and the analytical tools that are used to investigate them. We are very fortunate to have extensive education and experience on plastic failure analysis, and every year we deal with a large number of files involving these failures, which keeps us on our toes when dealing with these claims. So every investigation follows methodologies that are designed to generate questions and test hypotheses. This is done primarily to ensure that the results obtained are valid and that the conclusions and the opinions created are based on solid data and are derived from physical evidence available. As you can see in this chart, a key point in every investigation process is the evidence identification. From the evidence identification, everything else, all the way to the conclusion and the reports, stems from it. Unfortunately, the evidence identifications is sometimes overlooked, but we need to remember that the analysis and conclusions are directly proportional to what evidence is available. Like I said before, as the chart indicates, the rest of the investigation, traces back to the evidence available. I want to pause here for a second and emphasize that the process of evidence identification is organic. This means that one can sometimes go back to the site and verify that all evidence was documented and collected. However, in some or many cases, it is critical to properly identify the evidence quickly, and this job usually starts with you, the adjuster, and the emergency personnel on site. In this presentation, I will provide you with a few tips that have worked well for me when identifying evidence on site. And in this presentation, I will review cases involving plastic materials that can be found in the following components. So the first case will cover rubber gaskets, but it is also applicable to other components like rubber joints, rubber couplings, and tubing with rubber internals or the entire tubing made of rubber. The second case will cover CPVC fire sprinkler pipe, and that's that amazing orange pipe that we see sometimes in buildings' fire protection systems. I want to quickly review some analysis techniques that are commonly used in failure investigations involving plastics and polymers. Keep in mind that later in the presentation, I will show you how these techniques were used during that investigation. So the first one is visual and microscopical examination. And this is used to identify initial areas of interest. And in some cases, this technique can help provide all the answers needed to arrive to a conclusion. A very common technique we use in forensic engineering or failure analysis is the scanning electron microscopy, or the SEM, which is used when features that we want to see require higher magnifications, or that they need the use of other techniques that tag along with the SEM, and which can help us understand the composition of a sample or a contaminant or an inclusion. When it comes to identifying plastics, FTIR spectroscopy is the main technique that we use. It is also used to determine the presence of fillers, foreign contaminants, and degradation. A good example where this technique is useful or helpful is when we examine claims involving food industry components, which, as you can imagine, require a high level of quality. In this image that I present here, the spectrum shows some small differences between the subject sample and the reference that we have. And this helped us identify small changes that were happening in the manufacturing process. Another amazing technique is gas chromatography mass spectrometry. I know it's a big word, but trust me, it's a very simple technique to analyze. Obviously hard to get it to work, get the sample to work in it. GCMS is a technique that combines the properties of chromatography with the detection of mass spectroscopy. So it is used to identify very small substances or small amounts of substances within a test sample. This technique allows us to identify small contaminants or small amount of contaminants that caused or contributed to a failure. An example of where this technique is used or can be used goes to identifying accelerants like gasoline in fire and explosion investigations, which many of you may be familiar with. Many other techniques are used in investigations, but remember that they all play an important role in discovering the root cause of failures. To illustrate the point I made before about evidence identification, I will use my first case, which involves the failure of a rubber flange gasket in a mechanical room, and this was in a high-rise building. In this case, the failed gasket allowed enough water to escape, and it damaged equipment in the mechanical room, the elevators, some of the units in the building. As you can imagine, the costs in this claim were in the millions of dollars. One of the questions that I get a lot is whether the evidence can be shipped to me. And well, I know that every case is different, but whenever possible, it is best to have your expert visit a site and completely inspect it to properly determine the root cause of the loss. When I visit a site, I keep an open mind and explore all possible causes before selecting and removing evidence. In this case, there were several possible factors that could have caused this failure and the flooding. I have dealt with several failed rubber gaskets in mechanical systems, and I know that it's crunch time during emergency work. And some of the involved parties, like the contractors in charge of the repairs, the original installers, the current service contractors, and sometimes even some adjusters, being pressed by the building or the tenants, tend to focus their attention and to blame the failure on what it is visibly damaged. So in this case, the gasket. Just keep in mind that when I refer to rubber, I don't necessarily mean natural rubber, but more likely one of the many, many synthetic rubbers that exist. As I mentioned before, this case involved a multi-million-dollar loss with a rubber gasket as the primary suspect. Also keep in mind that gaskets are found everywhere, industrial, commercial, residential, automotive, and that they can all be examined in a similar way. When it comes to installation or blaming the installer for a failure like this, obviously the installer is in many cases an easy party to blame. And indeed, in many cases, failures result from installation issues, but not always. Look at the picture here, and this arrow in yellow here shows exactly where the gasket failed. It's important to consider in an investigation like this, the entire assembly, the piping supports, hangers, not only to look at the flange and the gasket at issue. A review of maintenance and inspection records usually help me understand whether the manufacturer recommendations and the applicable codes or standards were followed. But I also have to keep an open mind and, and keep present that the standard of care, or keep present what the standard of care is expected from the contractors involved. Wear and tear is an easy choice when looking at a component that has been in service for long. However, sometimes the answer is more complicated and requires testing and a look at the history of maintenance and inspection in order to be able to clearly pinpoint it to age. In this particular case, this gasket, this joint was in service for only 6 months. So why has it failed? Well, as you can imagine, manufacturing defects are a favorite of many. And sometimes it's easy to forget that every material has its limitations and that components tend to fail when those limitations are exceeded. Several techniques can be used to determine the degree of degradation and its role on the failure. In this particular case, the plaintiff's expert tested a sample from an area that was showing visible signs of what they consider to be degradation. The SEM images and the FTIR results that they presented are shown here and are great examples of the use of examination techniques that we discussed before. However, to me, these results lacked depth and something else was missing. So I came up with a more detailed examination protocol. I always keep an open mind when trying to identify a failure mechanism. There are several potential reasons that could have caused or contributed to a failure like this, and it is my job to consider them all before coming up with a conclusion. In this case, the simple answer was yes, there were other potential causes for failure, and I will show that here. But first, I want to address the initial opinion of the expert for the plaintiff. In their test, and this is where their claim was based on, they only sampled a small area from the inner diameter of the gasket. This area was showing some degree of damage, as can be seen in this image. However, later on, we concluded that this was attributed to direct contact with the fluid in the pipes rather than a defect in degradation of the gasket. So what they did was they tried to draw a conclusion based on a single data point, which in my opinion is a classic example of scientific tunnel vision. One thing to keep in mind in gasket seals is that they have a large area and a volume that creates the seal. As you can see here, the entire on-plane surface of that gasket is creating the seal, not only the inner diameter. So one thing to remember also is that most materials exposed to water or other chemicals will degrade. The key here is not that they don't degrade, but that they don't have excessive degradation during their service life. My proposed testing included FCIR at different locations and depths along the gasket, and it showed that the degradation did not occur. So what really happened? Well, codes and standards need to be reviewed carefully. However, when we deal with mechanical installations like this one, codes and standards are not always very specific, and many aspects of the design and the installation are left at the discretion of the designer and the manufacturer of the system. As discussed before, my findings show that degradation was not a contributing factor. So what really caused the gasket to fail? Well, in a nutshell, the gasket selection was flawed. And during my review of guidelines for gasket selection, I discovered that the type of gasket used was wrong and led to the failure. This gasket was not rated for the pressure in this application. Gasket performance is influenced by a number of factors, and it includes the material used, the style, the thickness, the clamping force, as well as several other parameters. It was clear in this case that during the design phase, someone ignored or oversimplified the system conditions, or they simply copied and pasted general gasket selection and installation instructions for this application. In this case, you can see that human error by the design engineer was the cause of the failure, and it was we ended up tracing it back to the designer of the piping system. As you can see, the initial opinion of the plaintiff's expert incorrectly put the liability on the gasket manufacturer, who in this case I was representing. My investigation tied the root cause of the loss to the designer of the system. I'm going to move on to my second case today, and I'm going to be talking about plastic piping in fire protection systems. The fire protection systems are very well regulated. They are regulated by provincial fire codes as well as NFPA standards, or National Fire Protection Association standards. When it comes to inspections of fire protection systems in Ontario, the fire code is the minimum legislated requirement, and the NFPA standard is more involved, it requires more work, and it's not mandatory. So it's important in your claims to review carefully what the contract between the building and the entity doing the inspection or the maintenance is. So other provinces have different legislations and must be evaluated on a case-by-case basis. Today, I will focus on the failure of CPVC plastic pipe, but keep in mind that I am trained and experienced in dealing with all types of failures in fire sprinkler systems. Most commonly, the failures I see in these systems involve plastic or metal pipes, sprinkler heads, different valves, and freezing. CPVC, or chlorinated polyvinyl chloride, is used in not only fire protection systems, but as well in plumbing applications. And this means that it can be found in many buildings, even if they don't have a fire protection system. So why do CPVC pipes fail? Well, there are many reasons, and some of the most common are improper installation, contamination, incompatible chemicals, freezing, and manufacturing defects. In this case, I was retained to investigate a loss in an emergency room of a regional hospital. In this case, the equipment damages were in excess of $1 million, not including business interruption, which I'm not sure how it works in this case, being a public entity. Additionally, you can imagine that the downtime affected not only this community, but the surrounding hospitals as well. So a fracture on a CPVC pipe can have a very similar look, even if it results from a failure mechanism such as freezing, manufacturing defect, or environmental stress cracking, ESC. Careful analysis and evidence identification is required to determine the correct cause of that failure. The failed pipe in this particular case suffered from environmental stress cracking. So when looking at the fracture surface, it was clear that the crack had progressed from the inside towards the outside of the pipe. This was a clear sign that the contaminants were inside the pipe, and it allowed me to focus my attention on what was inside the pipe rather than taking the time to investigate what was outside. In CPVC pipes, ESC is typically created by incompatible oils, plasticizers, or glycols, and it creates a fracture pattern that is similar to what you see here on these images. So in many cases, visiting the site and identifying the potential source of these compounds is critical for every investigation. In this case, the analysis of the fracture surfaces using GCMS detected incompatible glycols, which were likely originating in the antifreeze solution used. As I mentioned before, analysis via GCMS detected the presence of incompatible glycols, and these glycols were traced back to the antifreeze solution used by the fire protection contractor. And remember that antifreeze solution is used in fire protection systems, but it has to be compatible when used in CPVC fire protection systems. In this case, it was not, and it caused the ESC and the water escape. Eventually, the investigation led to the contractor being named in this section, and this claim was settled before it went any further. So that was a good outcome there. So if they can fail, why are CPVC pipes used? Well, the metal pipes, which are the older style pipes, if you will, they also fail. But in this case, CPVC pipes offer lower costs and much easier installation and repairs. And what I want you to take away from my presentation today is the following information. And one is that evidence identification is key. Reviewing all possible causes is a very important part of the investigation process. Also know that, and this is especial for large and complex losses, which obviously we don't know if it's a large and complex loss or not a complex loss on the onset. But if possible, invite the third parties to the site before repairs are completed. This, it may sound like it slows things down, but believe me, it is a game changer in the long run. And also, an obvious cause of loss can lead you in the wrong direction. Even in those cases when it's obvious, other possible scenarios need to be explored and ruled out. And finally, trust your expert, but you can ask them challenging questions. And believe me that it feels great when you ask me challenging questions during an investigation. It really prompts a great conversation that ultimately benefits your claim. And with this, I am going to pass the screen to my colleague Dino Matei, who will be talking about metallurgical failures.
Good afternoon, everyone. Thank you for joining us for this presentation. I hope you enjoy it already, and I hope you enjoy the next section as well.
Hey, Dino, sorry, can I interrupt just for one quick second?
Sure.
Do you mind? Sorry, can I just get you to hit slideshow mode, bottom right of your PowerPoint? You look down, looking for an icon that looks like a slide projector screen. Up. You mind if I just take mouse control from you? There we go.
Everything's okay now?
Yes, perfect.
Okay, once again, thank you everyone for joining us today for this presentation. I hope you enjoyed our speakers, and I hope you will enjoy this presentation. I would like to speak more about interesting cases, but I do not have the time. I'm trying to get some cases that one might be interesting for you. This side of presentation is called metallurgical failures. However, I think a better word would be metallic material failures. Metallic materials are not only metals, but are alloys. And alloys are developed to enhance the properties and to meet the needs of certain applications like corrosion resistance, fatigue resistance, or strength. In my opinion, there are only 5 different modes in which metallic materials can fail. And this is supported by literature published by ASM International. And one of the most admired book, which is the Bible of failure analysis, is Understand How Materials Can Fail. So these are 5 modes that I'm going to mention. It's fracture, it's fatigue, it's wear, corrosion, and creep. There are a number of reasons why failures do happen. Service or operation conditions, improper maintenance, manufacturing deficiencies, design deficiencies, installation deficiencies, wear and tear, act of God, negligence, insurance fraud, break and entry, or revenge. I'm going to present you an interesting case involving a grain silo. And it's about a spout that failed. In this industry, the grains are lifted using an elevator up to a certain level from where they are spread through the grain silos. And they're spread through spouts. These spouts are designed in such a way that the grains are not damaged during their fall. And one of the design involves the use of a so-called retarder. Retarder doesn't mean it's a retarded thing. It means it just slow down the speed of the grains while they're falling on their respective silos. In this particular incident, one of the spouts fractured and caused significant damage to the area. We were notified about the incident a few days later, and by that time the site was cleared and the evidence was removed. And it's very important in an investigation to attend the site as quick as possible to document the site condition and the condition of the components of interest. Luckily, in this particular case, there were a few relevant pictures provided by the owner showing the condition of the spout. When we attended the site a week later, there was already snow, and most of the evidence that was not retrieved was covered in snow, and it was difficult to locate and remove it. However, we tried to do all the best to find the relevant components for the investigation. We used our drone department to document the condition of the elevator and the spouts at the top of the grain elevator. And as you can see on the left image, there are 3 spouts that are going down from the grain elevator to the respective silos, and the one in the middle is the one that fractured. Our groin examination also indicated some deficiencies with installation, like crisscrossing cables, which is a no-no in the industry because they can rub against each other and then they can wear out and they could collapse. Our drone investigation also really indicated that another condition which was not acceptable, like a cable that was rubbing against a sharp metal end. Following the incident, the evidence was removed from the site by the owner and stored inside. However, there was no scientific method to identify the components and to document them. So this was a hard task. And because this was a large loss, all the interested parties were invited to attend. It was the owner's insurance company, the installer insurance company, and the manufacturer insurance company. So there were 3 experts there, and we identified the components of interest, and we selected which would be suitable for further lab examination. As I mentioned earlier, these spouts are provided with retarder boxes. The retarder boxes are manufactured in a different place, and they are installed on site by the installer. And there are several welds which are involved in this process. And we identified that one of the weld was of interest. This is how the retarder of interest was firstly documented, and there are some images showing the weld that looked of interest. Upon further examination, it was found that the weld exhibited several deficiencies, insufficient weld and weld beads, which are not considered good conditions for a weld. During the examination, we also found a thumb buckle, which is shown in this image. And as you can see on the right image, it showed has been bent and fractured. So after we examined the weld and found the thumb buckle, and we said, maybe this would be the cause of the problem. So these thumb buckles are designed to take longitudinal loads. They are not designed to take lateral loads. So this fracture was of interest. So again, we provided a testing protocol to examine the thumb buckle. And that involved metallurgical evaluation of fracture surface analysis and chemical analysis. These images are taken under a scanning electron microscope, and they show relevant features of the thumb buckle. And in plain terms, it shows it was a brittle failure. But because the thumb buckle was heat treated, this fracture mode was considered not an issue. Those two images are showing a cross section through one of the threads of the thumb buckle, and it shows here that it was zinc plated, and the microstructure shows that it was appropriate for this application. So based on these observations, the thumb buckle failure was not considered of concern for this particular case. Then we moved again to the welds, and we found incomplete weld penetration, and as I mentioned earlier, significant weld beads, which are considered a no-no for welding. The weld was further examined under a scanning electron microscope, and deficiencies that were observed earlier were confirmed. Further metallurgical examination was conducted on the weld itself, and it showed that the microstructures were appropriate. Following extensive examination, the conclusion was that the collapse of the spout was the result of manufacturing deficiencies. It was a substandard weld with voids and significant beads. Other factors adding undesirable stresses to the structure were considered crisscrossing of cables and ice buildup, because the incident occurred in November after rain and ice buildup on the structure. And as I mentioned earlier, the turnbuckle failure was not a contributing factor, but the result of the failure. In complex investigation, one needs to look into all possible aspects. So it's not always possible to say how a failure occurred just by looking with the naked eye. You have to do certain steps, and these are very, very complex, and it involves a lot of lab work and participation of all the interested parties. Sorry. The second case that I want to discuss with you today is the tower crane collapse. This was a tower crane involved in the building of a structure in Toronto, and without the reason initially, it failed. Luckily, there was no injury and the crane operator was only scared. He did not have any injuries. But because it was theoretically associated with a personal injury, the Ministry of Labor was involved. So the site was not accessible for a couple of days until the Ministry of Labor finished their investigation. After the site was cleared, all the interested parties were invited to participate and try to collect the evidence. Because the incident occurred on a construction site, there was a lot of mud and a lot of the evidence was not available or it was not found. The incident occurred because a components called slew ring failed. The slew ring allows the crane to rotate 360 degrees, and it's held in place by 48 bolts. We couldn't find all the 48 bolts, but we found a few relevant ones, and they were taken to a lab for examination. And following examination by naked eye and under a stereo microscope, we determined that the bolts failed as the result of failure. Fatigue failure. Fatigue occurs when the bolts are either over torqued or underly torqued. And under the circumstances, it was irrelevant to determine if they were over torqued or under torqued. It was an installation issue. Further examination revealed the fact that the crane was 30 years old, and at that time in Canada, the tower cranes were supposed to work for maximum 25 years. Moreover, the tower crane was operated by an illegal immigrant without proper work permission. So at the end of the day, we provided an opinion to our client, which helped them to make a decision regarding the further subrogation action. I would like to present more cases, but I'm running out of time, and I would like to thank you again for your participation. And if you have any questions, please let us know. Thank you.
Thank you, Dino. Yes, we would love to hear more of these really cool cases. And it's always very interesting to hear you and Eduardo's stories. You guys come across very, very interesting claim scenarios. I'm going to take back the screen and have Dino and Eduardo's contact information on the screen. And we will just take a couple of questions just so that we stay on track with time. We're supposed to break in 2 minutes, so I'll just get right to it. First question for Eduardo is, fire sprinkler systems, when they freeze, we're always asked to have the pipe inspected to confirm. Not sure this is needed, but we comply. Is it very simple to conclude freezing as the cause?
Thanks. Thanks for the question. That is a very good question. The reason for it being so good is that, yes, it's very simple to identify if the pipe had failed, especially in metal pipes. If it fails because of freezing, it explodes basically in a few parts or a million pieces. The issue that I see is, what I believe needs to happen is that the insurance companies want to understand what else is behind that freezing event. If the freezing is because the heating to that area was not adequate, or the installation was subpar, or the glycol in those pipes was not inspected in time or replenished. So there is a number of scenarios that lead to failure by freezing, which are still considered a good avenue for subrogation. And you can your team can find the liable parties by doing an inspection on those conditions. Hopefully that answers the questions, but I'm happy to send or establish additional communications to answer more questions or in more detail.
I think it's great. Next question is for Dinu. In instances with large components and exhibits, such as the crane example, how do you manage the chain of custody and inspection of such pieces of machinery?
That's a very good question. This is very hard because when there are large components that fail, the first thing that the owners want to do is to clear the site and prevent damage or other consequences. So by the time we are asked to do the investigation, most of the components are removed from the site and they're not protected. But once we are there, we are trying to do all our best to make sure that the components are very well protected. And the crane failure that I mentioned, it's a good example. They wanted to clear the site after the Ministry of Labor cleared it, and they moved it to a yard. And it was close to the cold season, and the site was not proper for that preservation. Luckily, there was no damage caused to it, but as soon as we were asked to assist, we went there and preserved it as much as we could. So it's important to preserve the evidence well, and it's important for us to attend the site as soon as the incident happened.
So how do you typically have the adjuster put some sort of, like, how do they protect the components from the elements and from tampering and so on? What would be a recommendation for an adjuster or anyone that's managing a claim to be able to preserve the evidence sufficiently?
So adjusters are very well aware that the evidence needs to be preserved. However, sometimes there is a need for an engineer to assist. And my best advice is, if you have a large claim involving a large component, contact us as soon as possible and we'll advise accordingly. Each site is different.
Yeah, so it's kind of a custom advice depending on the circumstance.
Yeah, so coming back to this crane collapse, the most important thing was to preserve the remainder of the fractured bolts which remained on site. And basically it was a simple task. Just use some chlorine-free degreaser.
Cool. Great. Thank you, Dinu. Well, that gives us just a few minutes for a break before our last session. Thank you very much, Eduardo and Dinu, for the presentation. Folks, we're going to be taking a approximately 10-minute break, and we'll be commencing on the hour.